Okay, we're going to do 5.8 notes, simplify radicals, and solving equations with exponents. So here's your title. Go ahead and write this down. For solving when taking roots, if n is even, when you take the root, you need a plus minus in front of your radical, whatever your n value is. Remember, so if n is even, n could be 2, 4, 6, 8, 10, any even number here. If your root is odd, like 3, 5, 7, 9, and so on, then you don't need a plus minus. So that's what the difference between these two is. If your n value or your root is even, you need a plus minus in front when you take the nth root, and you don't need it if it's odd. So switching over, I'll show you where this applies. We're going to apply it right here. So we're going to solve each equation. Remember, just like we've always been doing, we solve for x. So in this equation, x cubed equals 64, we're pretty much already there. We just need to get rid of that power 3. To get rid of the power 3, the opposite of power 3 is the cube root of x cubed. But what we do to one side, we got to do to the other, like this. So what happens on the left side is the power 3 and the cube root, they undo each other, leaving you with just x equals. Then you have the cube root of 64. 64 is actually a perfect cube. So when we take the cube root of 64, you're really asking what times what times what is 64, and that happens to be 4. You can also plug that into your calculator, and you would see that. You can plug the cube root of 64 into your calculator, and you would get 4. Let's go ahead and do another one. This one has a bit more to it. So we want to get x by itself. We have to move the 3, the power 4, and the 6 over here where the 42 is. But what would you move first? Hopefully you would think to move the 6 first. So we're going to add 6 to both sides first. Those cancel. I have 3x to the 4 equals 48, because 42 plus 6. Now what do is I'm going to divide both sides by 3 so that these reduce to 1. I have x to the 4 left over. Equal sign. 48 divided by 3 is 16. Now we're going to undo the power 4. To undo that power 4, we need to take the 4th root of both sides. So what happens on the left side is these undo each other, leaving us with x. And the 4th root of 16, you can plug this into your calculator, and actually 16 is 2 times 2 times 2 times 2. So that means that the 4th root of 16 is just 2. But you know what? Let's go back here for a second, because we actually forgot to do something on this side. See how our root is 4? Going back to the previous paper, that means our root is even, because n is 4, and 4 is even. That means that in front of this 4th root of 16, what am I missing? A plus minus sign. So instead of just putting a 2 here, I'm going to put plus or minus 2. So I have 2 solutions to this problem. Did I need a plus minus in this problem? Well, what was my root? My root was 3. If my root is 3, that's odd. Well, odd does not need a plus minus. So this is fine as it was. But here I needed to put a plus minus on this side of the equation because I had an even root. Here's a few more problems. So now let's focus on the root for real quick. We're going to be taking a 5th root eventually. So do I need a plus minus? Well, because 5 is odd, I do not. Actually, this problem is pretty straightforward as well. All I have to do is take the 5th root of both sides, like this. The power of 5 and the 5th root will undo each other. We have the 5th root of a negative 1024. So make sure you know how to plug that into your calculator if you don't know it. So the 5th root sorry, the fifth root of negative 1024 is negative 4. Let's go to this one. This one is a little different than the ones we've seen before, because x is inside parentheses, and those parentheses are raised to a power. We will undo that power like we've been doing over here. Before we undo that power, though, let's go ahead and get this 2 over here. Now, we got to think about, what is this saying? This says 2 times x minus 5 cubed. What's the opposite of 2 times is divide by 2. So we're going to divide both sides by 2. What happens on the left side is these reduce each other, leaving us with x minus 5 cubed, because the 2's are gone, equals, okay, and then negative 16 divided by 2 is negative 8. Now, I'm trying to get x by itself. I cannot add 5 to this side yet, because this is kind of trapped by the power of 3. So we need the power of 3 to go away. So we're going to take the cube root of both sides. The reason why that works is on the left-hand side, the cube root and the power of 3 are going to undo each other, leaving us with what's on the inside, which is x minus 5. Bring down the equal sign. On this side, I have the cube root of negative 8. If you go into your calculator, or if you can realize that 8 is 2 times 2 times 2, but actually because it's negative, negative 8 is negative 2 times negative 2 times negative 2. That means the cube root of negative 8 is negative 2. But if you're not fully comfortable with this yet, I promise you, if you plug the cube root of negative 8 into your calculator, you should get negative 2. This becomes a very simple equation to solve. All I do is add 5 to both sides. X equals, and then negative 2 plus 5 is 3. Okay, sorry. So, there you go. Go ahead and copy down these exponent properties. You actually know some of these already. 4 and 5 might be newer to you, but go ahead and copy them all down. Okay. So you've copied them down, probably pause the video. Now we're going to go here and we're going to apply some of those properties we just saw. We're going to simplify these. I know my F on the word simplify is all messed up. So if you look at this one, I have 3 to the 2/5 times 3 to the 1/3. Well, what property would that be? Well, I'm multiplying 2 the same number with different exponents. That would be this first property right here, which means we're going to add the exponents. Well, how do you add 2/5 and 1/3? So we're going to do a little side work here. Side work. 2/5 plus 1/3. To add fractions, what do you need? You need a common denominator. Well, what's a common number that 5 and 3 go into? That would be 15. So to make this 3 into a 15, I would have to multiply it by 5. But what I do to the bottom of a fraction, I do it to the top, so I don't change the value of the fraction. I want to do the same thing over here. I want this 5 to become a 15. 5 times what is 15? Well, that'd be 3. But what I do to the bottom, just like I did over here, where if I multiply the bottom by 5, I multiply the top. Sorry, by 3. If I multiply the bottom by 3, I multiply the top by 3. So let's go ahead and let's bring all this down, make it look simple. In the first fraction, 2 times 3 is 6. 5 times 3 is 15. In the second fraction, I have 1 times 5 is 5. 3 times 5 is 15. And then now I can add these because they have the same denominator of 15. Well, 6 plus 5 for your numerators is 11. And then you just keep your common denominator. But what's the point of doing that again? Remember, think about what you're trying to do here. You're trying to combine or multiply these 3's that have the same, or sorry, that have different exponents. Well, we saw that, we had to add these. So, sorry, I'm trying to fit this in here. So this becomes 3 to the 11 over 15. So we did this work right here to get our reduced fraction right here. Let's go ahead and do the next property, or next problem. This one's in parentheses, and the only property I see that has parentheses is this one. So this one says if you have x to the a raised to the power b, you multiply the two exponents. So that's what I want to do here. I want to multiply 2/3 and 1/5. So let's go ahead and do a little side work here as well. We want to multiply 2/3 and 1/5. We've done this a lot in my class. We already know just to multiply your numerators and denominators. 2 times 1 is 2. 3 times 5 is 15. So this is our answer for this one. Let's go ahead and do the next one. Right here, I have 7 to the 1/2 divided by 7 to the 5/2. The property that this applies to is property number 3. So because we have the same number on top, or variable, in this case, we do have a 7 that's common here. I'm just going to subtract the powers. Subtract the top minus the bottom. So this becomes, let's see what happens here. This becomes 7 to the 1/2 minus 5/2. Okay, so we got to do what's 1/2 minus 5/2. So let's do a little side work here as well. Side work. 1/2 minus 5/2. Remember that subtraction is basically addition. So, what did I need here to simplify this? I needed a common denominator, so 15 in this problem. But if you look here, I already have a common denominator, don't I? I have a common denominator of 2. So right away, I can go ahead and combine this. Well, what's 1 minus 5? It's -4. And then what's my common denominator? 2. So this becomes 7 to the -4 over 2. Well, hopefully you can recognize that you can divide -4 by 2. So -4 divided by 2 is -2. There's something you need to make a note of. I forgot to write it down earlier, but you need to write this down right now, that you cannot leave negative exponents. And if you look here, that's what we're looking at right now. We don't want to leave any negative exponents. And so what do? Well, there's another property you wrote down a little bit earlier. I'm going to show you. You wrote this one down. X to the -a is equal to 1 over x to the a. So if I have 7 to the -2, the way I rewrite this is 1 over 7 to the +2. Just take a moment to think about what happened here. And, if it helps, look at the property I have as well. If you look at these, let me try to get these in the same frame. If you look at these, that is what happens. In this case, from the property I have x, but in the actual problem I have 7. 7 and 7, x and x. -2 becomes +2. That's true here as well, because -a became +a. And then 1 is on top. Okay, so that one you might need to digest a little bit. So, if you need to pause here. This is a good time to look at it and say, okay, what actually happened here? Now, you would be done here, but there is one more thing we could do. I know. Well, what's 7 to the power 2? Well, 7 to the power 2 is 7 times 7. And 7 times 7 is 49. So this becomes 1 over 49. And that's your final answer. Okay? All right, 2 more to show you. Then we'll be done with this one. We have the square root of 60. When we're simplifying radicals, we want to find perfect roots that go into each of these. So the square root of 60, well, think about what your perfect squares are. 1, 4, 9, 16, 25. You know these numbers. The biggest perfect square that goes into 60 is 4. It turns out that 4 times 15 is 60. So we can rewrite this as the square root of 4 times the square root of 15. Why would we do that? Because the square root of 4 is 2. That's it. Let's go ahead and do this one. With this one, it's a cube root of 16 x to the power 3, y to the power 9. I want to find a perfect cube that goes into 16. Well, what are our perfect cubes? 1, 8, 27, 64. But obviously 27 can't go into 16, it's too big. But what about 8? That can go into 16, right? So what I'm going to do is, actually, we'll get back to that in a second. Actually, the first thing I want you to do, is split up the 16, the x cubed, and the y to the 9 in their own cube roots. The reason why you can do this is because on the inside it says 16 times x cubed times y to the 9th. This is all still being multiplied, but they now all have their own cube roots. But like we just saw, 16 is really 8 times 2. I'm going to bring these guys down as well. I'll show you how to take care of those in a second. The cube root of 8 is 2. Now, look what happens here. We have the cube root of x cubed. That means that these cancel each other out, leaving us with x. What about here? So I actually want to go back to this real quick. You know how we say these cancel each other out or they undo each other? What you're really doing is you're dividing this 3, the inside 3, by the root 3. Well, what's 3 divided by 3? It's 1. And that, if you think about it, there's actually a 1 here. That's not a coincidence. So I want to apply that reasoning to this one. We have y to the 9, but we're taking the cube root of that. What we do is we just take 9 and divide it by 3, and 9 divided by 3 is 3. So what we have on the outside of the cube root is y to the 3. Again, I got that 3 by dividing this by this. Now that took care of this, that took care of this and this. Again, I'll show you where these came from. Let me use a different color. The 2 came from the cube root of 8. The x to the power 1 came from here. The y cubed came from this. But I have something left over that I didn't cross out, and that is the cube root of 2. Well, because I can't do anything with that, I just leave it right here. Let me just go ahead and rewrite this a little bit. I'm going to bring the 2 down. Instead of writing x to the 1, I'm just going to write x. I have the y cubed and the cube root of 2. Okay, let's see if we can do this last one. I think we can save this for later. So we're going to do the same thing here. Now this is 81 times x to the 7 times y to the 20 times z to the 13. So we're going to give each one their own 4th root. Switch colors here. So I have the 4th root of 81. I have the 4th root of x to the 7. I have the 4th root of y to the 20 times the 4th root of z to the 13. Okay, so I just gave each one of these their own 4th root. there is a fourth root of 81. If you look at your chart, the fourth root of 81 is 3. So that becomes 3. Now this one, like we did over here, you know how we divided 9 by 3 to get this 3 right here? If you divide 7 by 4, it doesn't divide evenly, but here's what you're going to do. How many times does 4 go into 7? It goes in there 1 time. So we're going to have x to the 1 on the outside. So we'll get back to that in a second. But how many do we have left over from here? If I divide 7 by 4, I have how many x's left over? 3. We'll come back to that in a second. What about y to the 20 with the fourth root on it? Well, 20 divided by 4 is 5, and it actually goes in evenly. So that's completely taken care of. Then I have z to the 13, but with the fourth root on it. So I'm going to do 13 divided by 4. But 4 doesn't go in evenly. But how many times does 4 go into 13? It goes into 13 3 times with 1 left over. So it goes in 3 times with 1 left over. So we're going to put our leftovers on the inside of a fourth root. How many x's did I have left over? I had 3. So I have x cubed on the inside here. How many z's did I have left over? I had 1. So I'm just going to put a z right here. I didn't have any y's left over. That's why I don't have any y's right here. I don't have any numbers left over, so that's why there's no numbers inside. So my final answer is 3x, y to the 5th, z to the 3rd, times the fourth root of x cubed z. And we'll stop there, and we'll just do that another time.